Okay, hi guys. So in this lecture, we'll be discussing about first we'll see some examples on sulfonation, and then uh, we'll be seeing elimination intramolecular. Okay, so let's get started. So one of the important examples here is we have a phenol, and if we pass actually, if you want to nitrate it, so we have concentrated HNO3 and H2SO4. So it will yield me something like this with NO2 attached on all the ortho and meta positions of phenol. Okay, but an interesting thing to note here is we would also be getting something like this. Okay, because this is a strong oxidizing agent, so this actually oxidizes phenol group. So this is a result of that only. This is a side product which we get unnecessarily. Okay, so this is one of the ways to approach the problem. The second way to approach the problem is if we can somehow restrict the formation of this compound by again reacting the phenol with the concentrated H2SO4. So what we will get is something like this. Now as this compound is already deactivated by the presence of two -M groups, this won't further will this won't further oxidize the phenyl ring. Okay, hence this formation of this side product or unnecessary product is been restricted. Okay, so what can we conclude is this, that due to sulfonation of phenol, electron density on ring, phenyl ring, actually decreases, and hence chances of oxidation of the ring is also very less, becomes less. Okay, and the formation of para benzoquinone doesn't take place. Does not take place. Okay, this is actually para benzoquinone. Okay, so let's now see another set of reactions called elimination intramolecular. Okay, so what actually happens in elimination intramolecular is we have what is called a tertiary butoxide, or beg your pardon, tertiary amine oxide. So we have something like this, and a good leaving group which is tertiary amine oxide attached to it. Okay, so what actually happens in this case is when we heat this compound, what actually happens is this oxygen attacks on this hydrogen atom to withdraw it from the carbon bond, and at the same time after this OH is formed, this nitrogen actually withdraws its bond pair from the neighboring carbon atom, leaving a positive charge here. Okay, and this O minus on attracting H leaves a partial negative charge here. So this is during the transition state. Obviously what will happen is this will go here, this will come here, and the bond will come between the two neighboring carbon atoms. So we will have something like this, and plus an Me2OH would be formed. Okay, Now let us look at the second example. We have something like this, where H is coming out of the plane, N is also coming out of the plane, positively charged, O minus is there, Me2 is there, pH is there, and we have also a second H attached here. So as you can see that as the 2H and NMe2O minus group is coming out of the plane, they both are spatially nearer to each other. Okay, so they both are spatially nearby, rather than this O minus and this H, which are on two opposite sides of a plane, right? So they are spatially distant. Okay, so what actually happens in this case is this O minus will attract this H plus, and thereby having a negative charge on this carbon atom, and as soon as O minus attracts H, the nitrogen actually withdraws its bond pair from this carbon atom, forming a carbocation on this carbon atom. Okay, and as the positive and negative charge are there on the neighboring carbon atoms, they will form a pi bond. Okay, so we'll get something like this. H is here, pH is here, and we have, you can name the OH and Me2 as the leaving group. Let us look at the third example. Here we have something like this. We have N plus here, O minus here, and we have H coming out of the plane and pH coming inside the plane. So what would again happen is this O minus will take H, as it is nearer to the H spatially, they both are in the air and both are coming out of the plane, hence this O minus and H will be nearer. I hope you can imagine the structure in your mind. So then what will happen is double bond will exist between this carbon atom and this carbon atom, and NMeO2 would be leaving the ring. So we have something like OH and Me2 as the leaving group. Okay, so let us discuss now the pyrolysis of ester, which is also based on the same concept of elimination intramolecular. We have pyrolysis of ester, in which what happens is we have something like this, an ester group, again this O minus actually attracts this H. At the same time it will result in the breaking up of this pi bond, and the lone pair will come in rescue the positive charge carbocation with donating its lone pair to form a bond pair. Okay, and this bond would be actually withdrawn by the O plus to create a neutral atom on, or neutral charge on itself. So what will happen is, and resulting as this H and C bond would be broken up, so this bond will be converted into a double bond between these two carbon atoms. So we would have something like CH2, C double bond O, OH plus CH2, double bond CH2. Okay, so what do you mean by pyrolysis? Pyrolysis is nothing but cleavage by heating. This actually requires some heating to be done. Okay, and estimate is 500 degrees Celsius. Okay, so this is called cleavage by heating. Okay, now let us look at the characteristic of this reaction. So we have either in the pyrolysis or in the elimination intramolecular, we have the intermediate as pyricyclic. Then we can say that it is a syn elimination, as we saw in the previous set of examples, that two nearby O minus and H were actually getting attracted to each other, thereby the C and H bond was getting broken up and the O and H bond was getting created or formed, and this was actually taking place when the two were on the same side of the plane. Okay, in our case, in the examples which we saw, they were coming out of the plane. Okay, third is more acidic hydrogen is liberated. More acidic hydrogen is liberated. Okay, so with this we come to an end of this lecture. In the next lectures we will be seeing halogenation of aromatic compound. Okay, so till then, good luck and goodbye.